Hi, this is Josh Camacho, and welcome to our educational series on MultiValue Databases. ZoomAssist is the owner and distributor of several multi-value platforms, including JBase and OpenQM. But this video series is designed for any of the multi-value platforms, including D3, Universe, U2, and others. In our first video of this series, Martin Phillips, a senior multi-value engineer, will discuss the differences of the multi-value model from the traditional SQL model, including the speed and flexibility that can be achieved by such a different model. We hope you enjoy the video.
Hi, I'm Martin Phillips from ZoomAssist, and today we're going to meet the data model that underlies multi-value databases. It's often referred to as the PIC data model because it was largely developed by a gentleman called Dick Pick and his colleague Don Nelson. Nothing in the computer industry lasts 50 years unless there's something really good about it, and multi-value databases have stood the test of time. So the relational database model is widely used by products such as Oracle and was created about the same time, and we'll use this as the starting point for our discussion. Relational databases store their data in the form of tables, much as we could draw on a piece of paper. For our discussion, let's consider a very simple order processing system. In this system, you might have a table that represents our orders. And this table will have rows and columns like any other table. And in here, then perhaps each row represents an order. And in multi-value terminology, the rows of a table are known as records. So each record represents a separate order, and there is no practical limit on the number of records you can have in a table. In multi-value terminology, the columns of our table are known either as attributes or fields, and we'll use the latter term through this presentation. So the columns of our table each hold information relating to a feature of an order. As an absolute minimum in a very simple order processing example, we need a date, perhaps, that the order was placed. We need to know who to place that order, so perhaps a customer number. We need to know what they've decided to come and buy from us, a part number perhaps. And we maybe want a quantity, so we know how many of them they have purchased. A real order processing system would need much, much more. So let's add an order to our table here. And we can see from the data that's on the slide now that in this example, on the 12th of December, customer number 1072 ordered part number 315, and he ordered 3 of them. And as time goes by, we would gradually fill up the orders table with further records that look very similar to that. Now we'll discuss later that we don't actually store dates in the form they're appearing in this example at the moment, but for now it'll do. Having got multiple orders into our table, we need some way in which we can identify any particular order. And traditionally in relational database design, you look at the data that is there and you say, what is there that uniquely identifies one row, one record from another? In this particular example, there is nothing. And so we create something that is naturally unique of our own, and this might perhaps be an order number. And we refer to this as the record ID, or the primary key. Now, as drawn in my diagram here, the record ID is not shown as being a column of the table, but is a handle by which we access that record. And that's a distinction that only becomes important when we start doing programming. For the purposes of this discussion here, we can treat the record ID as a column. And so I'm going to change my diagram just slightly, as we see here. What we've constructed so far is the way in which a relational database would store these orders. But of course a real order will have much more complicated data. And tables in relational databases are defined using a set of rules called the rules of normalization. Now, the only rule we're interested in is the so-called first rule of normalization, and that says we're not allowed repeated data. So if my customer comes into the shop not to buy, as my first customer here did, one part 315 and buy 3 of them, but he wants to buy multiple things, we have to find some way to represent that. Now, one possibility would be to change our orders table so that the records do not represent an order as a whole, but they represent a single line from an order. So here we can see that order 2241 now has 3 separate records with a suffix that identify which particular item this is. Now this is just one way in which we could get around that problem of how to store multiple items. Another alternative, and this is the one that relational databases normally use, is to break our database table into 2. So we have the top table shown in this diagram that holds information about the order as a whole, and we have the bottom separate table that contains information about the part numbers and the quantities. Now in a real database, this is going to get much more complicated, because a real database will have many subtables and much more complicated data structures. Dick Pick and his colleague Don Nelson decided to resolve the problem of repeating values in a different way. Instead of requiring the subordinate table, they chose to discard the first rule of normalization completely and say that a single entry of our table, a single cell of my table here, can contain multiple values, hence the term MultiValue Databases. So here we can see that order 2241 has now been brought back into a single record in our database. Now if you've come from a relational database background and are looking at this for the first time, probably thinking this is totally alien to the way in which databases are designed. No, it's just a different way to store our data. Notice that a multi-value database can store fully normalized relational data without any changes. Going in the opposite direction is usually very hard work. So let's add a little bit more terminology to what we know here. A field that can contain multi-values is known for obvious reasons as a multi-valued field. However, it is perfectly valid for a multi-valued field to have only one value in it. It's not reasonable, for example, to say to the customer walking into the shop, "Good afternoon, sir, you've got to buy at least 2 items because my part number field is multi-valued." Where 2 or more fields have a value by value correspondence, as in the case of our part number and quantity, they are said to be associated. And a real database table may have multiple associations. Perhaps we decide to allow our customer to pay his bill in stages. So here we've added a second association with a payment date and a payment amount. This is not saying that on the 14th of December he paid for his part 315s and on the 4th of January he paid for his part 319s. It is a separate associated pair of fields. Real databases, real applications may have much more complicated structures. The multi-value model lets us go one step further. The values in our table can be broken into sub-values. And as an example here, consider a situation where whenever we sell something, we have to keep track of the serial number of the item that we have sold. So here we can see that for the part 315, of which there are 3 in our order, there are 3 serial numbers. Our 319 has 1 serial number, and our 400s have 2 serial numbers. Now this is getting very complicated. Unfortunately, the sub-value level is not widely used in real databases. It's quite likely that we're all familiar with the multi-value database model from our everyday lives. When we do our weekend shopping in the supermarket, at the checkout we're given a till receipt, and that will have single-valued items, such as the date and the total value of the sale, and it'll have entries in it showing the item you have bought, the number of them, and the price. That piece of paper is a multi-value representation of our shopping. So, how is this data physically stored inside the database? Going back to the simple order that we started with, in our order 2241 in this case, the data that we need to store is the date in whatever form that we actually store it in our database. We need to store the customer number, we need to store the 3 part numbers, and we need to store the 3 quantities. So we can see those set out in black here under the table. Now in a multi-value database, everything is variable length. And so we need some way, as we look at this sequence of characters here, we need some way to know where one field ends and the next one begins. And what Dick Pick and his colleague did to achieve this was to insert in the gaps between each field a special character called a field mark, shown in this diagram simply as FM. So as we look at this data, we can see that the field mark between the date and the customer number identifies where one ends and the next one begins. And where we've got multi-valued data, as in our part numbers and our quantities, then a second mark character, the value mark, comes in, separating the values. Now we can see that by working in this way, our fields are truly variable length. We can have an empty field with two field marks next to each other. We can have megabytes of data between those two field marks. And our multi-valued list there with the part numbers in could have any number of part numbers. There is nothing about the data model that restricts us to some limited number. Note that there is nothing in our data structure here that tells us that the part numbers and the quantities are associated. This is the job of something called the database dictionary, a topic we'll discuss very briefly in this session, and we'll discuss in more details in a separate presentation. So what are these mark characters? We have to remember that this data model was devised over 50 years ago, and at that time the character set used by computers, only half of it was actually used. The upper half of the 8-bit character set was undefined. And so Dick Pick decided to borrow for his own use the last 5 characters in the character set. And he used these to represent our mark characters. The item mark we haven't spoken about here, and it isn't widely used. The field mark, value mark and sub-value mark separate the items in our orders example. And the text mark is to do with text processing and irrelevant to what we're discussing here. But the key point is that Dick Pick reserved the last 5 characters of the 8-bit character set for his own purposes. Now clearly real applications may want to use those in modern systems because the upper half of the 8-bit set now is defined. In many countries it contains the accented characters, particularly those common in European languages, but there are alternative definitions that are used in different countries. Now if we stay with the common one for the accented characters, we have a little problem here, that the 5 characters that Dick Pick has displaced are now not available. And the one that causes us the most problem is the sub-value mark, character number 252 from our 8-bit character set. Because this one not only is our sub-value mark, but it's also the German U umlaut. And so when we try to store people's names, Mr. Muller, with a U umlaut in his name, cannot be stored because he ends up as Mr. M sub-value mark Löhr, which is clearly not acceptable. We have to come up with some way around that. In some multi-value databases there is no special solution to this, and we simply have to transliterate his name to change its spelling. In other multi-value databases there are alternative encodings that allow us to handle characters outside of the normal 8-bit character set. Now we have a little problem. Here's our diagram again of this same order. We've got the mark characters shown in the diagram at the bottom of the page there. Let us imagine in our application we need to find the second part number in the order. We have no alternative but to start at the beginning of this character sequence and walk along looking for field marks, counting them until we arrive in the part numbers field, and then doing the same to walk through counting value marks for the items in this part number field until we find the one we want. Now thankfully that's done for us deep down in the database engine in a very cleverly optimized manner that makes it a lot faster than you might expect. There are many advantages to using the multi-value data model. Again, if we go back to our starting point, the simple order we've been working with so far, the order record contains the entire data for an order in a single record. Unlike a relational database where we'd have to be collecting the scattered components that the first rule of normalization has required us to create and reassemble the data for processing, only to take it apart again for any further storage. As a result of this, the multi-value model is usually faster than the relational model. Secondly, because there are fewer tables, the application is easier to understand, easier to maintain, it reduces development costs and development times. It's also easy to modify tables as changes are made to an application. Multi-value applications tend to evolve slowly over time rather than requiring periodic expensive rewrites. Earlier on we mentioned dictionaries in this discussion, and although we're not going to discuss them in great detail here, it is worth looking at just in principle what they are to do with. Every table in our application normally has a dictionary. So we have an orders table in this example we've been working on, and it will have a dictionary, and the job of the dictionary is to describe the orders table. If you come from relational databases into MultiValue for the first time, you may be familiar with the idea of a schema that describes the entire application structure in one go. The MultiValue databases just break this up so that each database table has a separate description in its dictionary. It's just simply another way to achieve the same thing. Normally there's a one-to-one correspondence between dictionaries and database tables, but we might have a situation where we've got two orders tables, for example, for different years. We've broken our orders up on a year-by-year basis, and if they are identical in their structure, the dictionary would be shared. The dictionary describes the structure of our data. It tells us which field is which. How do we know that the part numbers are in field 3? It describes how we convert data between the way in which we store it internally and the way in which a user might want to see it on their screen. It describes the associations between associated fields, and it sets defaults for the query processor that produces reports out of our system. There are in MultiValue databases two different ways in which the dictionaries can be structured. There are those that apply to applications that have come from a PICS type background, and there are those that have come from the prime information type background. And although they use different internal structures to represent their data, they are doing fundamentally the same job. What sometimes causes concern amongst MultiValue developers when they first move to this environment is that they find that there is no automatic validation of our data applied by the database. On a MultiValue database, you can write the customer's name into the customer number field without anything detecting it and causing errors. Now that is not really an acceptable situation. There are various ways around it, as we'll discuss, but there's a big difference between relational databases and MultiValue databases. In the relational world, we've got an application here that's working on something typed in by a user and storing it away in the orders file. In the relational world, data validation is done at the point when you write the data to the file. And so anything that's wrong will break that bottom link there as the data is to be written. In the MultiValue world, we take a different view. And we say, no, we'll do our data validation on data entry rather than on storage. It means usually that we have to do less validation. We're not repeating it over and over. But if we really want the mechanisms that relational databases offer, it is usually possible to implement those on MultiValue products. MultiValue databases are widely used in systems ranging from single user account systems to massive corporate databases. They've tended to become one of the computer industry's best kept secrets, but are becoming more widely known as a result of the growing acceptance of the NoSQL movement that is recognizing that the relational model perhaps is not the ideal for all situations. And a common reaction from people who've come from a relational model background who move to MultiValue when they first meet this is to say, wow, why didn't I know about this? Well, now you do. This is Martin Phillips from Zoomasys.
Thank you, Martin, for explaining the MultiValue database model, and it's important to remember some of the differences from the SQL model. MultiValue can often be faster than SQL, thanks to its ability to store complex data in a single table. MultiValue data is all variable length data, and therefore is not typed at the database layer. Data is defined with dictionaries on each file, rather than a schema for the entire database. While we touched on this topic here, we'll go into it further in another video. MultiValue systems perform data validation at the application level, not the data level. This allows for validation to be handled where the business logic is written. And finally, MultiValue systems can read large and complex records quickly thanks to performance tuning at the core of its database engine. These are just some of the differences of the MultiValue model over the SQL model. If you enjoyed this video, please subscribe to this channel. And if you'd like to discuss MultiValue further, reach out to us. We love MultiValue and are always happy to discuss it. I'm Josh Camacho. Thanks for watching.